In this program, textiles. First, silk. Then fabrics that protect us from the cold. And finally, grafted fabrics. According to Confucius, silk was discovered 2,640 years before Christ. One day, a cocoon fell into Princess Xiling Shi's teacup. She unwound it, revealing the famous silk thread. By dint of observation, the Chinese learned everything about the silkworm. For centuries, they kept the origins of the wondrous cloth a closely guarded secret. Of all the natural fibers, silk has always been considered the most valuable. But the high cost of producing it makes it essentially a luxury product. Commercially, the most widely used silk is raw silk. Raw silk comes from the dried saliva of the Bombyx mori silkworm. This silkworm, totally domesticated, feeds exclusively on the leaves of mulberry trees. Mulberry leaves, meted out in 4 meals a day, are placed over the caterpillars who climb up on them and devour them. About 30 days pass by between the time the eggs hatch and the cocoon is formed. Larval development consists of 5 stages separated by 4 moltings. During this period, the caterpillar's weight is multiplied 10,000 times. After the last molting, the silkworm moves to the straw provided and begins to make a cocoon. It spins an oval casing of raw silk as a protective covering in which it remains until it becomes a pupa, an intermediate stage between caterpillar and butterfly. After approximately 15 days, the pupa is metamorphosed into a butterfly. Silkworm breeders let out only a small number of their butterflies so they can mate and supply them with eggs for the following season. Once detached from their support, the cocoons are ready to be reeled. A cocoon comprises a single continuous thread that can be up to 1 kilometer long. The thread is composed of 2 filaments of a protein called fibroin. The 2 filaments are bound together by a stiff natural glue, sericin. To soften the sericin, the cocoons are placed in water at 90 degrees Celsius, where they are beaten with small brushes to disintegrate their outer layer, the burr. The burr consists of individual strands that are more or less broken. The ends of the intact strands are thus extracted. The raw silk is then thrown or twisted and doubled to achieve various strengths and thicknesses. It goes through a threader, which assembles the ends and glues them together to form a strong thread. The thread is then wound in a loose coil called a skein, from which it is wound onto bobbins or reels. The silk is now ready for weaving. The principle of weaving always remains the same, regardless of the fiber or machine used. It is the art of forming a fabric by interlacing warp and weft threads at right angles. The warp, or lengthwise grain, runs down the length of the cloth as woven. The weft, or crosswise grain, runs perpendicular to the warp. The warp threads are guided through groups of parallel wires, or heddles, fixed side by side so they can be moved together at the same time. The warp threads are held under tension and raised or lowered alternately to create a shed through which the weft thread is inserted with a shuttle. Each time the shuttle carrying the filling yarn goes through the shed from one side to the other, The yarn left by its passing is beaten forward by the reed against the tied-in knots at the cloth apron. As it comes off the loom, the exquisite woven fabric is inspected closely. Now the printing process can begin. To produce silk scarves, for example, the fabric is fastened to a long table so that up to 50 scarves can be printed at the same time. A stencil is developed photochemically on a polyester gauze, which has been stretched over a rectangular frame. A stencil is made for each color in the design. The frame is placed on a stationary rest. As the fabric moves sideways on the table, a doctor blade inside the frame scrapes the color paste along sideways. Where the patterns are engraved on the gauze, the color is deposited on the silk square. The operation is repeated until all the colors are printed. The printed fabric is then dried directly by heating. A steaming process ensures color fastness. The steam swells the fibers and the water concentrates the color in each fiber. The domestication of the silkworm has made it a fragile animal, totally dependent on human intervention. This insect is, however, an excellent biological model. Researchers are considering transferring foreign genes to it. Because of their remarkable silk-producing system, the genetically engineered worms could synthesize on a large scale such biotechnological compounds as vaccines, hormones, or antibiotics. Until just recently, the finest natural silk was produced by the Bombyx mori, or mulberry silkworm. Today, petroleum and plastic microfibers are finer than the finest silk. Fabrics woven with these fibers have a host of applications. Among others, they can help keep us warm. Clothing today does more than merely protect against the cold and rain. Sportswear and hiking clothes are now designed to meet very specific criteria of comfort. They must prevent heat loss while keeping water out and letting perspiration pass through. At an ambient temperature of about 30 degrees Celsius, an unclothed body is in a state of thermal comfort. The body's metabolic rate offsets any heat loss. The metabolic rate is the result of all the chemical reactions occurring in the body. But when the temperature drops, a person's metabolic rate is no longer able to make up for the skin's heat loss. A whole series of physiological reactions against the cold is set in motion. The first is vasoconstriction. That is, the constriction of the blood vessels in the skin. This curbs the flow of blood, hence heat to the skin. It causes an overall cooling of the surface of the body, most keenly felt in the face and extremities. The limbs can easily withstand a drop of 10 degrees Celsius. Through this phenomenon, the blood concentrates the heat inside the torso, in the vital organs which can tolerate only small variations in temperature. Another mechanism to fight off the cold is cutis anserina, or goosebumps, which contracts tiny muscles at the base of our body hair, causing each hair to stand on end. This thickens the layer of warm air which normally covers the surface of the body. It is this layer of air that insulates the organism from the ambient cold. However, if the air outside is both cold and windy, that protective air layer breaks up and the body becomes considerably cooler. This explains the wind chill factor. When there is wind, the temperature felt by exposed human skin is much lower than the real air temperature. But our body's natural resistance to the environment has its limits. Once it has lost a certain amount of heat, the body's temperature will fall. Ideal clothing will maintain body temperature near 37 degrees Celsius without exertion being required. According to scientists, a garment's insulating potential comes mainly from the layer of air it traps. Research has therefore mainly been focused on producing synthetic fibers capable of maintaining a thick airspace next to the skin. Synthetic materials that breathe and are water-resistant have also been developed. Clothing's insulating property decreases when it gets wet with rain or when perspiration is trapped inside it. In addition, a sensation of cold is produced when the sweat trapped inside the clothing evaporates. These drawbacks are particularly pronounced in such natural fibers as cotton or wool, which absorb perspiration. Waterproof sweat-transmitting fabrics, on the other hand, are intended for use in cold and wet conditions. These fabrics are used to make sports and hiking clothes and sleeping bags as well. To test their effectiveness, researchers use a series of lab tests which simulate the transfer of heat between an individual and a given environment. This device is patterned on human skin. It simulates heat and sweat transfers between the body and the environment. A level surface that sweats and is heated to 35 degrees Celsius is used to measure a fabric's insulating potential and permeability. Tests are also conducted using a thermal dummy with movable joints, which reproduces such human activities as walking and pedaling. The dummy's body is divided into 35 parts, each individually heated with electric resistances. This maintains a temperature comparable to that of the human body. Body heat loss can thus be simulated without taking sweat into account. Thanks to the thermal dummy, a garment can be tested under various conditions in an environmental chamber. Inside the chamber, temperature, ventilation, and humidity can be made to vary from one extreme to the other. The advantage of the dummy is that it helps researchers study the climatic conditions the clothing is intended for. It also enables them to measure the rate of air penetration through a garment's apertures, the sleeves for instance, and reduce losses caused by a garment's shape. A human subject may also be asked to test a garment or a sleeping bag within the enclosure. The advantage, of course, is that he can convey to researchers his physiological and even psychological impressions, although they may be subjective. Today, synthetic waterproof sweat-transmitting fabrics provide qualities of comfort under extreme weather conditions, something conventional textiles could not. In textiles, the latest technological innovation is grafting. Chemical grafts at the level of the fiber's molecules produce fabrics whose qualities and applications are as numerous as they are amazing. Modern technology has allowed the textile industry to become extremely diversified and to branch out into brand new sectors of activity. Special use of textile materials can be found in fields as diverse as aeronautics, nuclear energy, agriculture, public works, even healthcare. The new applications are in part made possible by a procedure called grafting. Grafting gives fabrics custom-made properties. A natural or man-made polymer textile is used to get the grafting started. Polymers found in all fabrics are chains consisting of a very high number of repeatedly linked structural units. First, the polymers are activated by electrons from a particle accelerator. This produces chemical fractures along the polymers and renders the fibers highly reactive. The substance to be grafted, or monomer, is placed near the polymer so it will bind with it. The monomer bonds firmly to the fibers of the material. This first grafted monomer triggers a polymerization reaction. The other monomers bond to it firmly in turn to eventually form a side chain fastened to the initial fiber. Chains of varying lengths are thus attached to the original fiber. These chains are what give the fabric the sought-after property. For example, grafting antiseptic monomers onto a polymer produces self-sterile fabrics, also called biotextiles. This kind of grafting gives the fabric long-lasting protection against bacterial attack. In a microbiological test, only the biotextile square is not invaded by the colonies of germs. In addition, the bactericidal agent grafted to the fabric does not diffuse outside because it is firmly bonded to the fibers. These properties make biotextiles particularly attractive for the manufacture of hospital clothing and self-sterile surgical dressings or public sanitation. In the technical field, grafted textiles are also efficient ion exchangers. These exchangers are cellulose filters to which is grafted a specific monomer which serves to trap a given chemical. In this arrangement, the grafted cellulose filter was designed to capture dye molecules. Indeed, the monomer has a particular affinity for the dye. As a result, the solution comes out of the filter purified. One application of this process is the dye-trapping bag of grafted cotton fabric. Several articles of the same color, which are liable to run when washed, are put into the bag. The bag lets the detergent in, but absorbs the dye, thus preventing the other articles in the wash from being stained. Increasingly, ion-exchanging textiles are being used to detoxicate effluent contaminated by nuclear, metallurgical, and chemical waste. Other textiles having special uses provide protection against fire and heat. They are fire-retardant textiles. Some fire-retardant fabrics consist of heat-stable fibers. These fibers do not ignite and conserve their main mechanical properties at temperatures above 250 degrees Celsius. They are used to make the protective clothing worn by firefighters and steelworkers. Other materials consist of conventional textiles treated with fire-retardant agents. Researchers use a variety of setups to test in the laboratory the flame-resistant properties of these textiles. To test fabrics used to make the garments worn by welders, for example, molten metal is splashed onto a strip of fabric. The rise in temperature of the inner side of the fabric, the side that is in contact with the skin, is then recorded. The object of the test is to count the number of drops required to obtain a 40 degrees Celsius rise in temperature. For home furnishings and some items of personal apparel, fabrics have to meet stringent flame-retardant standards. Tests are conducted with a lit cigarette and a flame simulating that of a match. The fabric is fastened onto a seat. To be accepted for domestic use, the fabric must not burn for more than 120 seconds. The development of new textile technologies has revolutionized the ways fabrics are used. Chances are we will soon be able to buy all sorts of new products, such as biotextile socks, grafted with an antifungal agent, which will prevent fungoid dermatitis and other foot infections. And what's in store tomorrow? Conductor fabrics? Anti-radiation textiles? The things now going on in the labs may well have our heads spinning someday.